Let me check. I think there should be sound now, because my laptop. Okay, yeah, now they can hear me. Yeah, because my laptop. So there's.
Have they confirmed?
Yeah, they have confirmed because my Okay, great. Sorry about that, because my laptop mutes itself in addition to Teams, so I have to unmute my laptop on Teams.
So let's briefly run through this.
Yeah, let's briefly run through the entire thing again. I was just motivating why it is relevant to prepare these and to study these quantum Gibbs states, which is studying condensed matter systems in an out of equilibrium. It is an essential resource in quantum semi-definite programming algorithms, which have a square root advantage over classical ones. It is used in quantum Boltzmann machine algorithms, which rely on efficient sampling of these distributions. And there's a proven quantum advantage for local Hamiltonians. That is, if your quantum Gibbs states comes from this local Hamiltonians that the authors of this first reference construct, you can, formally prove that these are hard to sample classically. And to understand how to prepare these things quantumly, I'm just going to quickly recall how we do this classically. So again, this is the classical Gibbs distribution at some inverse temperature beta. And the way you'd sample this classically is through the Metropolis-Hastings algorithm, which simulates the dynamics on a Markov chain, which goes something as follows. You start at a state, say, E, and then at every move, you pick a move with some probability PA, and then you transition to a new state, say A, with a probability given depending on the move, which is AS to S prime. And you weight, importantly, you weight this transition probability by this factor gamma here, which depends on the energy difference between the states you're transitioning between. And because you're doing this weighting depending on the energy, this is guaranteed to converge to the Gibbs distribution because it satisfies the detailed balance condition, which is given at the bottom. This is a stationarity and reversibility condition that ensures that if you run this process of transitioning states in the Markov chain, you will eventually, after a period of burn-in, be sampling precisely from the Gibbs distribution you want to sample from. So there is a quantum version of precisely this process, but it can be improved for a few reasons. One of them is that the way it works is that you are, say, at a state, now it's a quantum state in this Markov chain, and you do a local unitary moving to another state. And then you want to do something called boosted quantum phase estimation to find the energy difference between the state you've transitioned to and the original state. There's a few issues with this. One is that this boosted quantum phase estimation is said by the authors of the second reference not to be possible. So this is a criticism they make of the paper that proposes this. And the other is that since you have a quantum no-cloning theorem, if you don't transition to the new states you've gone to, you have to rewind to the previous states, and there's an overhead in doing this, which is done using the so-called Marriott-Water's algorithm. So instead of doing this, where you just directly quantize the procedure, we're going to instead consider a continuous version of this, where now probabilities are no longer discrete. We're going to work with continuous probabilities. You still have this gamma here, weighting the transition by the energy difference. But now the process is basically continuous. You no longer have an accept and reject term. You have a transition and decay term, and you have a diagonal negative part that ensures that these sum to zero. Well, and this dynamics is generated by this generator L here, so that the distribution at the time t will be the exponential of t times L times the initial distribution. The fact that this sums to zero preserves the probability pi zero, so that every time you have a probability distribution. You can quantize this to obtain something called a Davis generator, where the transition, so basically you no longer have a probability distribution that you're evolving. Now in the quantum realm, so you're going to be evolving a density matrix, and your transition term becomes conjugating this density matrix here by these A's, which are called jump operators. And then you subtract the decay term. And you can see here that if you take the trace of this, it's going to be zero. And this is the operator version of the sums of these two terms being zero, so that the trace of the density matrix is preserved. And again, you still have this weighting here, gamma, that gives the weighting depending on the energy transitions. And I'm going to explain what this B here is on the next slides. But before I go to that slide, just to make the remark that this takes the form of a Lindbladian, which you might already know, describes open quantum Markovian dynamics. Okay, so as I was saying, this Davis generator will describe the evolution of the mixed states, much like that generator did for the classical probability. And this B here I was commenting on the previous slide is just the Bohr spectrum of the Hamiltonian, which is the difference between all the energies of the eigenspectrum of the Hamiltonian. And when we do things quantumly, we also have to define a projection on the sector of the Hamiltonian, which corresponds to this energy transition. So this Hamiltonian here, this generator here, the Davis generator, satisfies a quantum version of the detailed balance condition. So it is guaranteed to converge to the Gibbs states we want to prepare. The problem here is that it is not really implementable. So if you wanted to take this and actually run this, we can't really do it. And the reason is because there is, if we wanted to, the problem is that to implement this, so notice that mu A is given by these projections on the sectors that do an energy transition from EI, EJ. This is not really possible to implement because it assumes infinite accuracy in the energy. And as you know, there's an energy time uncertainty. So if we had this infinite accuracy, we would need infinite time to actually run this and to prepare the Gibbs state. So there's a no-go in just taking this and implementing these dynamics to prepare the Gibbs state. One remark before I go to the final slide is that what we're defining here is essentially a Markov process on the energy eigenspectrum of this Hamiltonian. And if you express these operators AA, which are called jump operators in the eigenbasis of the Hamiltonian, this is what it looks like. This energy difference here, the transition that this jump operator is doing to the Hamiltonian will be precisely given by the matrix elements here that is responsible for the transition between an eigenstate corresponding to EI to EJ. So this is the picture you should have in mind.
So this is hard because of these projectors, but you could project not an eigenstate, but some energy window of some width.
You just described this last. That's precisely what we will do and what people do. Okay, so this operator with the projections can be expressed precisely like as an infinite time integral. And you can't really do this because the integration window is infinite in time. But instead, as Latko was mentioning, instead of like trying to resolve the energies with infinite precision, you choose an energy window. And this translates into, instead of defining this A news here, you instead define, which are the jump operators, you define some LA news, which are instead called the Lindblad operators, which are derived from the AAs by choosing an energy window given by an F of t, and integrating that instead. And F of t is going to have finite supports, so this integration window will no longer be infinite. And now, again, as Latko was suggesting, we are no longer transitioning to like a specific, we are no longer performing a specific energy transition, but we are transitioning in a window of energies. Okay. The problem is that in doing this, we in general be breaking the detail balance condition. So we want to engineer this Lindbladian here, which will no longer be the Davis generator, to still satisfy at least an approximate version of the detail balance condition by doing a careful choice of the filter function and the other Lindbladian components. Since this is now an approximate version of the detail balance condition, we also want to bound the distance between the steady states, which the dynamics will converge to, and the Gibbs states. We also need to bound the mixing time, right? Because if this dynamics takes infinite time, then it's also or an exponential amount of time, then it's also not really useful to us. And then finally, if we actually want to implement this in a digital quantum computer, which is something we also wanted to explore, we need to discretize and control, essentially trotterize this dynamics and control the associated error. So this is what we're going to be doing next. Okay, I'm doing okay on time. So just to give you an idea how we work with this quantum version of the detailed balance condition. So in practice, this is defined in terms of the special inner product. So if you recall that the usual Hilbert-Schmidt inner product is given by the trace of a matrix and its adjoints multiplied, we instead work with the Kubo-Martin-Schwinger inner product. And this is not unique. There's different inner products you could use to try and ensure that the Lindbladian satisfies the detailed balance condition. This KMS inner product is given, it's similar to the Hilbert-Schmidt inner product, but now it is interspersed with the square roots of some density matrix sigma. So the sigma dB condition will be defined as you being able to bring the Lindbladian across the adjoint of the Lindbladian across the inner product, such that this equation is satisfied. Because if this is satisfied, then you can ensure that sigma, and sigma will be our Gibbs states, or the approximation thereof, it satisfies this. And you can just follow the equations. Here you have the Hilbert-Schmidt inner product, but if you replace instead this inner product, you can bring this to the other side while leaving an identity behind, because there will be some cancellations here. And then you can ensure that this is zero, which implies that the Lindblad operator applied to the sigma you chose is zero, which means it is a steady state. So it will converge to this sigma once you do the dynamics. And the mixing time, we also need to define, which is the time it takes to converge to the steady states, is just the infimum of the time the dynamics takes to converge to the steady states up to some error. And we will also have to choose this error. So the mixing time depends on the error. So we need to choose a filter function that will filter these energy transitions I was talking about. The one we choose is a Gaussian with an window of delta E equal to square roots divided by the inverse temperature, or square root times the temperature. And the reason we choose this is because under the ETH, we have an entire derivation of this in the paper. It means that the energy transitions induced by the jump operator that we will filter will be captured within the energy window that is defined by this filter function. And by choosing this, we can also ensure that the transition term, which is the second part here, satisfies the sigma beta detail balance condition. An important thing to remark here is that by doing this, let me just check if I have this in the next slides. Yeah, so maybe just first talk about the ETH, which most people in the audience should probably know. But it essentially says that in a system satisfying the ETH, the expectation value, so if you express an observable in the eigenbasis of the Hamiltonian that satisfies this, it will take the following form. So the diagonal of this matrix in this eigenbasis will be given by function A of the energy, while the off-diagonal terms will be given by a random matrix ensemble that is weighted by a smooth function divided by a density of states that goes to infinite when you increase the size of the system, so it's exponentially suppressed. And again, I'm repeating myself maybe a bit, but under the ETH, we can show that this dissipative term of the Lindblad satisfies this sigma beta detail balance condition, and thus, and this is important, under the ETH ensemble, we can show that the Gibbs state is a stationary point of the Lindbladian, and thus the dynamics will converge to it. An important point that I wanted to emphasize is that we do not need to impose any conditions on the coherence term of the Lindbladian dynamics. And this is something that the original paper that proposed this algorithm, which is, I don't have it here, but it's this Chen et al. Paper, they had to engineer this term to make certain things coming from this term cancel out so that the detail balance condition was satisfied, while we do not need this term. So we are able to simplify the protocol under these conditions.
But the H has to satisfy the ETH.
It does.
That is a condition.
That is a condition, but we don't have to include it. Yeah, okay. Under these specific conditions, we can satisfy it. Not in general, we cannot.
So the AA is a transition matrix between every pair of eigenstates.
It's just could be a polynomial. So it will induce transitions between every pair.
Oh, but you don't care what it is.
No. We can in particular choose polys to be in this transition matrix. And this will induce the energy transitions. In fact, that's why they're called jump operators.
So it could be any local observable.
I'll get back to you on that. There's some conditions, but it is more permissive than otherwise you. So the ETH also simplifies the choice of these AAs.
It has to be an operator that satisfies this.
Well, yeah, basically, yeah. Okay. So we've chosen the filter function, and we have shown it to satisfy the sigma detail balance condition. But we also have to bound the mixing time. And we know from the literature that you can bound this time by the spectral gap of the Hamiltonian, which is the minimum real value of all the eigenvalues of the Lindblad. And so if you bounce this this delta L and show it to be polynomially scaling, then we have a bounce that's polynomial in the mixing time. What's in here we don't care so much about because there's a logarithm suppressing it, and this is at most exponential. On top of that, we also want to bound the distance between the Lindbladian under the ETH average and a specific instance of the Lindbladian, because that's effectively what we will be using to drive the dynamics. And if we do both these things, bound the distance between the ETH average and the Lindbladian and the Lindbladian spectral gap, we obtain this bounds on the mixing time, which is polynomial. The infinity norm of H, unless you choose a very pathological H, will be polynomial. And we also have a condition on the number of jump operators, which scales as the square of the system size times the inverse temperature to the sixth. Though in practice, we see that this is quite loose, and in our numerical simulations, you don't need that many jump operators. And I also was saying that we need to bound the distance between the states that the dynamics converge to and the Gibbs operator. And this is the bounds. Again, we have a sensible polynomial bounds with another condition on the number of jump operators, which is similar to this one. There's more details about this entire derivation in Appendix C of our work, but just to give you an idea about how it goes, it basically relies on mapping this dynamics to a classical Markov chain and computing the conductance of the Markov chain, which is kind of like a measure of how connected it is. But I will not go through the entire thing in this presentation. So this is the theory, or the theory about using ETH to bounce these dynamics. I will now present some numerics for the mixed fields Ising model. Which should be known to most people, but we will be so this is the phase diagram of the model, where you have a transverse field, which is associated to this X poly term here, and a longitudinal field, which is associated to this Z poly terms here. And we want to probe points at which the model presents chaotic behavior following the ETH, and points where this is not the case. To diagnose this, and this is what these plots show, we will use the fractal dimension of the Hamiltonian, which is a measure of delocalization of the eigenstates of the Hamiltonian across the entire spectrum. So we pick 3 points to study. One is
this like the IPR? How is this defined?
It is similar to the IPR.
So what's the definition?
So it's something like the IPR for the eigenstates, but then you take a distribution of something like the IPR across the entire all of the eigenstates, and then you have the expectation value of that and the variance of that distribution. And if you have a high expectation value but low variance, means that most of your eigenstates are delocalized, so you have chaotic behavior, and otherwise you have more regular, maybe even integrable behavior. And we pick we pick more than 3 points for our dynamics, but in the main section of the paper, we only present the results for 3. which would be a chaotic point, a point that we call regular, and also the transverse fields Ising model, which is known from the general literature to be integrable and free fermionic. So you can derive lots of analytical results about this point of the phase diagram. So these are results for the dynamics. So on the x-axis, we have the evolution time, while on the y-axis, we have the distance between the state at time t and the Gibbs states he wants to prepare. We see that, and we also define thresholds after which we consider the state to be prepared. We picked, maybe a bit arbitrarily, that to be 10 to the minus 2. So here, and this is what these lines, these vertical lines here, indicates the time at which this threshold is reached. We see that the chaotic point presents a fairly regular behavior with much faster convergence time than the regular points. And you can even see that for 8 qubits, we were not able to conclude the simulations here because they were taking that much more time.
Sorry, but why do you call it? Can you go back to the page?
Sure.
Why do you call this a regular point? If that model, the model is in principle still chaotic there, right?
Just because as diagnosed by the,
this measure shows it's way less chaotic than the
yes, it's the definition or our choices was guided by this measure of delocalization of the spectrum. But yeah, there's nothing special to say about this point as compared to like the transverse field Ising model, which is very special.
Even something like R might show, like when the longitudinal field is so large compared to the transverse field.
So the regular point has the longitudinal field like no, sorry, this is mean.
So like
it's like 6
big,
or 7.
like yeah. So
Okay.
yeah, exactly. Yeah,
it's quite large. Okay. It's regular because the spectrum is close to classical.
probably. So these plots show the scaling of the mixing time for these 3 points and different choices of jump operators. We see that again the point we call chaotic is much more well behaved than the points we call regular. We couldn't even say get a line for this for 5 jump operators. Though surprisingly, or maybe not so surprisingly, the transverse field Ising model is not that ill-behaved at all. Probably because there's much more structure in this model, and there's even a paper recently that looks at these dynamics precisely in free and quasi-free models, but they're outside the scope of, like, this is outside the scope of our results, but it doesn't behave that badly either. And we see the polynomial scaling in the mixing time with the increasing number of qubits. Kappa is the slope of this line, and polynomial like decrease in the spectral gap. So these things are related. Before I move on, just to emphasize that it turns out that the choice in the jump operator or the number of jump operators doesn't scale that badly. You see that these lines are almost collapsed. So it turns out that we don't need that many jump operators to get nice results, even though the scaling I had shown here is beta to the 6.
Sorry, but what was, can you go back?
Yes.
What is the message here? Because this kappa seems relatively similar in all 3 cases.
Yes, but the regular point is shifted, and the behavior is much more erratic. So the main point is that this middle column here,
yeah,
works as we expected. The other ones are, I guess, a bonus, just to say that there are points where you might get something that's much more erratic, but maybe in other points, even though our results don't encompass them, you still get fairly regular behavior.
But for instance, I don't see much difference between the first two plots.
No, exactly, but that's what I was mentioning. The transverse polarizing model still behaves quite well, even though it doesn't satisfy the ETH. So there's other different reasons why it should behave that well. And there are results in the literature that study specifically free models, but these are outside the scope of our work.
And they're mixing time scales in the same similar way as in a chaotic model?
Yes, I think this paper even shows it to be logarithmic. Even though this is not what we have here. So it can be even better from study.
Yes, is this critical, the critical Ising point?
Yeah.
Yeah, so it's the degrees of freedom will kind of delocalize, right? So maybe these mixing operators are like local
Or
flips, right? So they're kind of
that's
very different.
just move on a bit because I also wanted to talk about implementing this as a quantum circuits, because this is also something we are very interested in. At Continue, we have digital quantum computers, and we are always interested in examining whether we can actually go and implement these algorithms on our quantum hardware. And also, we wanted to do a noise study of how this algorithm behaves under noise. And to do that, we need circuits that we can derive from this dynamics. So the way we do this is basically successively trotterizing the different components of this dynamics. So again, we have essentially two components, two main components. One is the coherent part of the evolution, and the other is the dissipative part of the evolution, which comes from, this term of the Lindblad gives you the coherent parts, and this term here gives you the dissipative parts. So we trotterize this to begin with. So we split these two terms, and we implement it as a quantum circuit in the following way. The coherence term, we can just implement just an exponential of a Hamiltonian. Of course, with the Hamiltonian, then we have to further trotterize, like the polys. It will probably be composed of, but we can do this. The other term, the dissipative term, we actually have to define an operator VAI to implement, which will be defined in terms of an operator kappa, which is a dilation operator. And you can show that if you trace out this, and so this kappa is defined on the number of qubits of the system plus one ancilla qubits. And this single ancilla protocol appears in the literature in these two papers that are cited here. And if you define this kappa, this K operator on n plus one qubits, you can show that if you trace out the ancilla qubits, then you get precisely the dissipative parts of your evolution plus some error delta t gamma. And gamma is that weighting of the dissipative term that weights the transitions. Precisely this. And then on top of that, you also have to, because K involves these Lindblad operators, you have to, well, and these Lindblad operators are defined in terms of integrals. You have to discretize the integral, which is basically done using a quadrature rule, and then bound the error of that. And again, all of these steps come with an error associated with it. And to ensure that we don't ruin the states we converge to, we bound the final error, which is the distance between the steady states of the dynamics and the target Gibbs states, which is given by this here. The only cause for worry here would be this BH here, which is the Bohr spectrum of the Hamiltonian, but this is exponentially suppressed, so we are good. Okay, yes. One thing I did not mention is that we employ a randomized protocol in doing this, because if you recall the Lindbladian, there's a sum over A's, but in practice, we don't implement the sum over A's. We instead sample at each step one term from the sum weighted by a probability that is gamma A. And this still will converge to the correct Gibbs state. So one last thing I wanted to talk about is numerical results of simulating these circuits with noise. So we have two things here. On the left, there are some theoretical results that we derived on this noise. And this is assuming a global depolarizing model, which means after each application of one Trotter step of our circuits, we just globally depolarize we apply global depolarizing channel to the entire system. While on the right, we have numerical results using instead a depolarizing channel on every 2-qubit gate. Oh, this equation has seen better days, but you can see that we can bounce the error in the steady states rho infinity, and infinity is just because you're going to infinity time, so it's the steady states and the Gibbs states. And this is bounded on this is a bound given by the noise strength lambda here. B is just the distance between your initial states and your final states, and this lambda appears both as the numerator of this fraction and also in the denominator via u0, where alpha is just the convergence speed of your dynamics. So we have this theoretical bound on the convergence under noise, but we also have these numerics here. And we have the plots where on the x-axis we have the noise 2 qubits gates depolarizing channel strength, and on the y-axis we have the distance between the steady state of the dynamics and the Gibbs state. And we see something that's, it's perhaps not that unexpected, but it's nice to get some numerical quantification of this, which is at low noise strengths, using a larger Trotter step tends to be better precisely because this larger Trotter step has a lower error, because you have less gates in your circuits, so you will have less noise. So at higher noise strengths, and this 10 to the -4 for you to get an idea, current continuum machines are about, say, 5 to the -3, also like tending towards 10 to the -4. So this is where we get odds in terms of physical error rates. It is actually better to use a larger Trotter step, just because you have less gates in your circuit, so you have less noise. But as you increase the noise strength, there will be a crossover where using a smaller Trotter step will start being better. So implementing this in the machine, you have to model your noise as well as possible to try and optimize this parameter here so that you incur the least penalty as possible in terms of noise. Now, this theoretical bound here I was telling you about is using a global depolarizing channel, while this one here is using a 2 qubits depolarizing channel. The bound on the left is presented in as a dotted line on the plot, and you can see the numerical results are always below the bound. But something interesting that we found is that if we sort of like map the 2 qubits noise probability to the global noise probability using this formula, which essentially says what's the probability of 1-2 qubits noise, 1-2 qubits error happening, and you take 1 minus that, which is like probability. I'm probably mixing this up, but basically this maps a global channel to a 2-qubit channel, and you can see that if you, instead of like actually using the actual number of gates, you have this as an optimized parameter that you fit, the functional relation fits perfectly our numerical data. So this strongly captures the actual noise, the noise effects in our circuits. So I'll just conclude by summarizing our work and our contributions. So we used ETH to improve on Lindblad's protocols in the literature for quantum Gibbs state preparation. As I was mentioning, this simplifies the choice of the coherence term, which we can even like do away with, just to remind you of this. So this term here, if you're not using a Hamiltonian that satisfies the ETH, has to be carefully engineered to cancel out contributions coming from this term so that the detailed balance condition is satisfied, but we already satisfy it even without having to make these choices. So it simplifies the implementation of the circuits. And it allows the use of single poly jump operators, and this is also what you answered. And we also probabilistically pick the jump operator at every step. And this is something that other people did in the literature a few months before our paper came out. So unfortunately, we cannot claim full novelty on this. But it is something we have also done. And as I was mentioning, this protocol simplifies implementation of quantum Gibbs states on preparation on near-term devices. And I believe ours was the first numerical results using a realistic noise model of this state preparation procedure. And thank you so much for your attention. I'm happy to take questions. Yeah, I'll take a look at the chat soon. Yeah.
So the Chomsky composition you did, that was a first order.
The second order.
The second order.
I didn't actually do the second order.
Okay, yeah, I just didn't know if you get any advantage from going for the second order. If you
Yeah, we yeah, use it.
Yeah.
Go ahead.
So yeah, well,
Yeah, there's also a question on the chat, but
maybe you can do that.
No, you can do.
I guess what I wanted to ask is like the choice of jump operators. What are you actually looking for when you choose, like even between the values, right?
Something as simple as possible. That's too much. Like the poly is like actually like the best case scenario. But if you want to implement, it just needs to satisfy those conditions, and that's will give you the balance you want.
But the fact that it doesn't work